Hi everyone, and thanks a lot for clicking on my talk, which is going to be about do pulsar timing arrays observe a dark sector phase transition? A topic that is really close to my heart because I studied it for the last almost 5 years now, starting from my master thesis under the supervision of Felix Karlhöfer and eventually also doing my PhD under Kai Schmidt-Hoberg at DESY, which I recently finished, after which I then moved to Uppsala University, where I'm now recording this video. All right, let's get started. So there's a problem. We only understand 5% of the energy content of the universe. The other 70% of its dark energy and 26% is dark matter. And we have no clue what dark matter is. We know that it must be there due to some pieces of evidence from the CMB, from galaxy clustering, from the bullet cluster, but also from galactic rotation curves. Still, so far, we have only had null results in our direct detection experiments. So we still don't know what dark matter is made of. Now, however, things might have changed. In July 2023, there was a lot of news about a particular topic, which was pulsar timing. Pulsar timing arrays detected gravitational wave background. And now we might use this as a tool to find out what dark matter actually is. So how can we do this? First of all, let me discuss what a pulsar timing array is, and then come to how we can use it to find out what dark matter is. So first of all, you can imagine a pulsar timing array as basically us on Earth observing pulsars, which are somehow a little like galactic lighthouses. They turn, they have these cones in which they emit strong radiation, and if Earth observes them, we see flashes of light. These light pulses are very regular due to the high moments of inertia of these pulsars. So we can make a timing model for the pulses. And if there's some deviation from it, we know that something must have happened between us and the pulsar. So one example for a process that might change this is gravitational waves, which then might lead to these timing residuals. However, there are many other processes which can also have the same effect, which are these timing residuals that we observed for the past order 20 years, which is, first of all, the pulsars themselves can have strange effects. They can slow down, and also our clocks on Earth, they can go wrong. Also, we can have a mismodeling of our solar system center of mass, which is called ephemeris. But however, now since 2023, pulsar timing array collaborations excluded all of these explanations with more than 5 sigma evidence. However, they found they have found evidence in favor of a gravitational wave background with 3 to 4 sigma evidence. So that's quite something. Now, the question is, what is the source of this new signal? There's one standard null hypothesis, which is supermassive black hole binaries, which explains the signal to some degree. However, there's a slight mismatch between the numerical simulations that people run and the actually observed gravitational wave signal, which is somewhat too strong, and it also has a spectral tilt, which does not quite match what we expected from astrophysics. So, me as a cosmologist, I asked the question, are there possible other signal sources potentially coming from the early universe? One of these sources are first-order phase transitions happening in the early universe plasma. You can imagine this as in everyday life, a pot on the stove where you have bubbles in water which form, which then expand. Now in the early universe, they expand up to the speed of light, then collide and eventually give rise to strong gravitational wave background. Now this could be seen, for example, with LISA, but also we could have already seen it now with pulsar timing array measurements. So let's zoom in into the plot here on the right a little, into this red region, where we can see these nanograph so-called violins. So that's the signal that pulsar timing arrays found. Now I put on top of this an example for what a signal from a first order phase transition would look like. It has this characteristic broken power law shape, and there are three main quantities that go into this into the computation of this signal. One, alpha, which tells you how strong the first order phase transition is, and in order to explain the pulsar timing array signal, we need super strong supercooling, so alphas of over 1. Then we need slow phase transitions, which means beta over h parameters of 10, which means that the transition happens over a time scale of at least 1/10 of a Hubble timescale at that point. And that point in time is when the universe had a temperature of 10 MeV, or some billion Kelvin. Now, there's however a problem, which is that there's no such first order phase transition in the standard model. The question, however, is whether precision cosmology forbids it. So if there could be some BSM physics which actually requires such a first order phase transition to happen. Let's look a little into what happens in the early universe at these times. So around MeV temperatures, Big Bang nucleosynthesis happens. So this is when the early element abundances form, when neutrons and protons combine into hydrogen and helium. Now, there's a theory how this works, which is called Big Bang nucleosynthesis in the lambda CDM, or standard model of cosmology. And basically, it only requires the standard model particles. So there's you can explain the observed early element abundances if you believe that the standard model is true. Same is true for the cosmic microwave background. Also for that, you only need the standard model, including its 3 neutrino generations. If you had more of these neutrinos or neutrino-like species, dark species if you wish, this would make the universe expand faster and make the early element abundances different, and it would also make the structure of the multipoles of the CMB different. So we can exclude that there are more dark species after a given point in time, which is here the Big Bang nucleosynthesis. Now, turning this around again, we know that there cannot be such a strong first order phase transition during BBN, but what if it happens before? We basically only need to get rid of the energy density released in this first order phase transition, such that everything reheats and lambda CDM cosmology can just continue after that. That's basically the starting point for where my PhD also started. So what we start with was a very, very naive description of how such a phase transition could have happened. We assumed, well, it happens not in the standard model, but in a dark sector. So when I say dark sector, I here mean something, an extension of the standard model, which has no portal couplings. So basically a complete separate thermal bath. And if you say that the energy is released in that first order phase transition, it also therefore needs to stay there. So there's a super large contributions to N effective, which we call delta N effective, the deviation of, so the contribution to this N effective parameter, which is much, much larger if you want to explain the pulsar timing array signal than what is allowed by BBN and the CMB. Maybe more importantly, we also found that if you were to explain the gravitational wave signal and want to circumvent these delta N effective constraints, you would need super large bubbles, which we called Hubble bubble sizes. So bubbles which are almost the size of the observable universe at that time. That, however, comes with its own problems. For example, that processes with Hubble bubbles would violate causality. We don't quite know how to compute the gravitational wave spectrum from those processes. And also, that is a new thing. We don't know whether there might have been a production of primordial black holes associated with these super large bubbles in the early universe. Okay, but this was only a very naive fit. we found a way around it, which is that the dark sector needs to decay to standard model particles. Back in 2023, we assumed that the dark Higgs, so the particle that has this phase transition, can decay into pairs of photons at that time. When this happens sufficiently early, so before BBN, if the lifetime of this dark Higgs is below 0.1 second, we can actually find that the gravitational wave data can be explained even better than just with supermassive black hole binaries. However, at that point, we only considered this to be like a model-independent statement. We didn't write down a specific model for in which this statement is true, whether dark Higgs can decay to photons so early on. Now, several things have happened since then, since July 2023. First, there has been new pulsar timing array data, which shift the gravitational signal to somewhat higher frequencies, and also the slope has decreased a little. There might be now a solution to the final parsec problem in astrophysics, which would tell you that so the final parsec problem originally stated that there wouldn't be any significant amount of gravitational waves from supermassive black hole binaries. Then now there has just last month been a study which showed using n-body simulations that supermassive black holes are still unable to account for the full gravitational wave signal. Another thing more on the theory side is the investigation of more specific dark sector models, which I will come to in a second. And one thing that we studied in the past was to put more constraints into our analysis, more than just delta and effective. Okay, so let's see how can we include these constraints into our analysis chain. What we did is we used the Gambit framework to combine BBN data, cosmic microwave background data, data from direct and indirect detections. We include a likelihood for the bullet cluster and beam dump experiments, all under the framework of Gambit, which is used for global fits. So when you try to fit many data sets at the same time. Now, considering only a very minimalistic dark sector setup, as has been done in the past, let's say, few months, because there has an explosion in these kinds of studies, if you only have a dark Higgs and a gauge boson in order to turn the transition first order, you run into basically two problems we found. So if you have a portal coupling between the dark sector and the standard model, which you need to have in order to get rid of the dark sector energy density, you can achieve this in two ways. Either you have a Higgs mixing. This, however, is generating a mass term for your dark Higgs boson, which means that it messes up the vacuum structure of the dark Higgs potential, which then leads to only a fine strip in parameter space, giving you first order phase transitions, and therefore a large degree of fine tuning is needed. Or if you alternatively try to dump the energy from the dark sector in the standard model using kinetic mixing, you're also screwed because this decay of dark Higgs bosons to electrons is suppressed by a factor of the kinetic mixing parameter to the 4. And this is in tension with beam dump experiments. So we really need a different kind of dark sector model setup, and that is what we did in the past few months. So what we did is we added a dark matter candidate to this minimalistic dark sector setup, and we said that we consider a conformal dark sector, so without any mass terms and without the Higgs mixing term, which would in turn also lead to an effective mass term after the electroweak symmetry breaking. In that case, the thermalization between the two sectors, the dark sector and the standard model, becomes easy because of the scatterings of this dark matter fermions with standard model electrons, which is only suppressed by factor kappa squared. Now, if we combine all of this in our global fit, so the CMB data, the BBN data, beam dump experimental data, bullet cluster constraints, did I say direct and indirect detection experiments? Probably not, it's a lot. We found actually a best fit point for all of this, which can give rise not only to 100% of dark matter, but can also give rise to a signal on top of the supermassive black hole binaries that explains the pulsar timing array data better than only assuming supermassive black hole binaries. At the same time, there's a negligible impact on BBN and the CMB. There's no impact on, so it wouldn't be observable with direct and indirect detection experiments, and also the bullet cluster has no relevant constraints on this. However, with the next generation of beam dump experiments, which is if LDMX happens, we are actually able to test this model in the lab because it has a dark photon with a mass of a few hundred MeV and a kinetic mixing parameter of 10 to the minus 4, which is within reach. Let's look at what needs to happen before BBN for our best fit point. So the first order phase transition happens around 40 MeV through the nucleation of bubbles, which then collide, emit gravitational waves, and later on explain the pulsar timing array data that we observed today. Then at 7 MeV temperatures, the dark sector and the standard model decouple from each other. After that, the dark matter freeze out happens, and there's a small abundance of dark Higgs bosons, which later on decay during BBN, leading to some changes in BBN in the element abundances, which, however, unobservably small. So we don't change how BBN works as in compared to lambda CDM. Now, however, what now happens if in a few years LDMX, the beam dump experiment, tells us that the found parameter region with kappa being roughly 10 to the minus 4 is no longer feasible if this is ruled out? Well, we considered now a separate model in a separate analysis where we also allow for a dimension 6 operator, which allows phi to electron-positron decays before BBN. And in this case, we can find a nice explanation for the PTA signal, again on top of the supermassive black hole binaries, where, however, now the kinetic mixing parameter can even be 0. So this will be then harder to test, but possibly one could test this by studying constraints from supernova data. Okay, let me come to my conclusion and summary. So we've seen that even though we are only at the dawn of gravitational wave cosmology, we are already able to test pre-BBN temperatures, so above MeV temperatures, which so far have always been the limit of what is achievable, what can be reached. Then we've seen that pulsar timing arrays observed gravitational wave background, which can be explained by just having supermassive black hole binaries, but if you add dark sector phase transition on top of it, you get a better fit. We performed this global fit, including the PTA data, cosmic microwave background data, the BBN data, and lab data, and found that we have a best fit scenario, which can even be tested with next generation beam dump experiments. So it's quite exciting. And with this, I want to thank you very much for your attention, and I'm happy to answer all your questions in the upcoming discussion session. Thanks a lot.